Hello, now we continue with sequences, and today we shall consider several examples. I'm doing examples from the book or similar to them. Finding limits. Okay, first let's do this. Look at the sequence a sub n, which is 3n plus cosine n, all this divided by 4n plus 10. N grows to infinity, and we have here a strange term, cosine 1, cosine 2, cosine 3. It's very undetermined. Nevertheless, we can compute the limit by using the squeeze theorem. So I shall factor n from top and bottom. Usually we factor the highest power, and this is first power. There will be 3 plus cosine n over n on the top remaining, and below, when you factor n, you have 4 plus 10 over n. Now reduce by n. We can write our general term, 3 plus cosine n over n, 4 plus 10 over n. Now, what happens here when n grows to infinity? Is there a limit or not? We know that 10 over n will approach 0. What about cosine n over n? It also approaches 0 because of the squeeze theorem. I can write cosine n, no matter what is n, it's always between -1 and 1. So we divide by n the three sides of this inequality, and there will be -1 over n less or equal cosine n over n less or equal 1 over n. Look at the two sequences on both sides of cosine n over n. -1n approaches 0, 1n approaches 0, so cosine n over n is squeezed between these two, it also has limit 0. So I can write cosine n over n has limit 0 when n grows to infinity, and it can be on the top anything that is restricted between -1 and 1, or between any two numbers. Going back to our sequence, I can compute the limit. It will be 3 plus 0, 4 plus 0, which is 3/4. This is how we deal with our sequence, by using the squeeze theorem. Another example, look at the sequence a sub n, which is 6n plus n squared over 1 plus n. When we have such a quotient polynomial of n over polynomial of n, we factor the highest power, and on the top it's n squared. To factor it out, we have 6 over n plus 1. Below we factor n. It will be 1n plus 1. Reducing by n, I can write this n times 6 over n plus 1. This is one sequence here. This sequence that multiplies n has limit 1. 6 over n approaches 0, 1 over n approaches 0. And this quantity here comes closer to 1. n itself grows to infinity. N grows to infinity. 6 over n plus 1 over 1n plus 1 approaches 1. All the sequence n times with this expression will grow to infinity. So this is the result. A sub n grows to infinity, diverges to infinity. That's the term that we use in mathematics. The sequence diverges to plus infinity. So it does not have a limit, it's divergent. However, it's good to write infinity here instead of just say it's not convergent, because it gives you more information about the behavior of the sequence. If you just say it's divergent, well, no specific information. If you say it's diverges to plus infinity, it tells you something about the behavior of the sequence. Okay, here is another example. A sub n is 5 times square root of n over square root of n plus 10. Now we have here n to power 1/2, fractional power, but it works the same way. We factor this. On the top it's practically factored, 5 square root of n. If you factor this in the denominator, there will be 1 plus 10 over square root of n, reduced by root of n, and on the top we have now 5, 1 plus 10 over root of n. 10 over root of n approaches 0. N grows to infinity, and we have 10 over infinity, which is 0. So all the sequence will approach 5 over 1 plus 0, which is simply 5. The limit is 5. Moving to the next example. Look at the sequence. A sub n is 2 plus 0.8 all this power n. How to study this sequence? To compute limit here, we have to remember something from the previous lecture. Remember this. If x is whatever number with absolute value less than 1, then the consecutive powers approach 0. And here we have a number 0.8, which is obviously less than 1 in absolute value. The consecutive powers will approach 0, so we can tell the limit immediately. This will be 2 plus 0, which is 2. 2 converges to 2. It is a constant, doesn't change. The limit of 2 is 2. Okay. Here another sequence which uses the same basic sequence. A sub n is 4 power n over 1 plus 9 power n. Such exponentials here. So what to do? When we have exponentials with different bases here, we factor the fastest growing terms. So we shall factor 9 power n from denominator. And I shall write this way. On the top, there is nothing to do, but here I shall write 9 power n in front, and there will be 1 over 9 power n plus 1, like that. Then we shall rearrange it this way. I shall write it 4/9 power n, so 4 and 9 I'm uniting, and there will be 1 over 1/9 power n plus 1. So I'm actually rewriting the sequence in appropriate form. Now I can tell that 4 over 9 power n will approach 0. 4 over 9 is less than 1. 1/9 power n also approaches 0. Now we can compute the limit of a sub n. A sub n will approach 0 multiplied by 1 over 0 plus 1. 0 times 1 is 0. So the limit here is 0. And this is the correct way to organize your work. write the sequence in appropriate form so that we can use our basic sequence. Maybe one more example of the same nature will be helpful. Look at the sequence a sub n, which is 2 power n plus 3 power n, this divided by negative 3, n plus first power plus 4 power n. How to deal with this? On the top, 3 power n grows faster than 2 power n because the base is bigger, and below 4 power n is growing fastest, so I shall write it this way: 3 power n factored out, and there will be 2 power n over 3 power n plus 1 on top. Below 4 power n is factored, and we have negative 3 n plus first power over 4 power n and plus 1. Now we can rewrite this way: 3/4 power n. On the top here, 2/3 power n plus 1. And here we have negative 3/4 power n, and one negative 3, one factor negative 3 is written separately, and all this plus 1. So look at this. All the sequences that participate have limits, we can evaluate them. 2/3 power n approaches 0. 3/4 power n approaches 0. Negative 3/4 power n also approaches 0. So we can compute all these limits, and using the limit theorems we can write that the limit of a sub n will be 0 multiplied by 0 plus 1 on top, and below we have 0 times negative 3 plus 1. So this will be 0 multiplied by 1, which is 0. It's important in all these works not to divide by 0. So we can multiply by 0 but not divide. So this arrangement is the proper way to solve this problem. Okay, let's try this. A sub n is 3n plus 5, and here we have in denominator root n squared plus 1. Now we have this radical below, and it's not quotient of polynomials, but it's some sort of similar. Again, we have to factor highest powers. On the top, the highest power is n, so it factors easily, like that. What will be the highest power in the denominator? Let's do this. We first factor n squared inside the radical, like that. Then we distribute the radical to n squared and to the rest. There will be on the top n times 3 plus 5 over n. Here below we have square root of n squared, which is just n, and another square root, 1 plus 1 over n squared. We can reduce by n. A sub n becomes this: 3 plus 5 over n, and we are left here with square root 1 plus 1 over n squared. Here all the participating terms have limits which we can compute. 5 over n approaches 0, 1 over n squared approaches 0, so the limit here will be 3 plus 0 square root 1 plus 0, so this is practically 3 over 1, which is 3. Although we have infinity over infinity, it's not appropriate to use L'Hopital here because you have to differentiate this radical and it will not become simpler. So this is the best way to solve the problem. factor the highest power carefully from outside, from inside the radical, and then reduce by n. Now look at this sequence. A sub n is natural log n plus 1 minus natural log n. It's undetermined infinity minus infinity. It's not the quotient to use L'Hopital. What we have to do is very simple. We just have to unite the two logarithms in one. So I can write it natural log n plus 1 over n, which will be even better to divide by n inside, so it becomes natural log 1 plus 1n. And then I can use the fact that the natural logarithm is continuous, and I can write limit a sub n, which will be limit natural log 1 plus 1n. Because it's continuous, I can bring the limit inside. This will be natural log limit 1 plus 1n, and limit 1 plus 1n is 1, because 1n approaches 0, so the result is natural log of 1, which is 0. Okay? The difference of these two infinities happens to be 0. So I mentioned that for continuous functions we can do this. Let me remind you of the property that I'm using. If f of x is continuous at x equals a at some number, then limit f x sub n equals f limit x sub n, actually continuous on some interval, at some number, because the limit x sub n can be any number, and then suppose x sub n approaches a, so limit f x sub n will be f limit x sub n goes inside, it will be f of a. So if x sub n approaches a, if function is continuous, we can do such things. Other sequences. Look at this. A sub n is exponential to power 2n n plus 2. All this is in the power of the exponential. N grows to infinity. What is the limit? So I'm writing limit a sub n equals limit exponential to n or n plus 2. Exactly like in the previous case, because the exponential function is continuous, I can bring the limit inside the function. So this becomes exponential limit to n over n plus 2. What is the limit here? Look, you can write 2n n plus 2 this way. 2n over factor n in denominator, 1 plus 2 over n. Reducing by n, it can be written 2 over 1 plus 2 over n, and the limit is 2. So this limit on the top is 2, and here is our result. The limit of our sequence is e squared. Another example. Let's say a sub n is nth root of 3. What happens if n grows? So this is a sequence square root of 3, third root of 3, fourth root of 3. I can write this like 3 power 1/n. What will be the limit? To understand the limit, it's good to use the exponential function again. And I can either stay with this base, or I can just write exponential 1/n natural log 3. And it practically becomes the previous example. Limit a sub n, bring the limit inside the exponential function, will be exponential to power limit logarithm 3 over n. Because logarithm 3 is constant, this over n will approach 0. The limit is 0. This is e 0 power, which is 1. So nth root of 3 approaches 1 when n grows to infinity. And in the place of 3 we can put any positive number. If a is any positive number, take consecutive roots of a, e approaching 1. This is one interesting limit. It's good to remember it. Even more, look at this sequence. A sub n is nth root of n. N grows, but also the index of the root grows. So it's written n to power 1/n. When n grows to infinity, what will be the limit? Okay, again, going through the exponential function, I'm writing exponential, here 1/n, natural log of n. And it can be written exponential power natural log of n over n. And limit a sub n will be, bringing the limit inside, will be exponential power limit natural log of n over n. So we have to compute this limit. Limit natural log of n over n. It's infinity over infinity, undetermined form. I remember this theorem for functions, so I can extend our sequence to a function, and this will be limit natural log of x over x when x grows to infinity. And here, for functions, we can use the rule of L'Hopital. Differentiating top and bottom will be limit 1 over x over 1 when x grows to infinity, which is limit practically 1 over x when x grows to infinity, and this is 0. 0. We know this for limits of functions. So the limit of our sequence is 0. Going back to our computation, I have exponential 0 power, which is 1. So let me write this again. Nth root of n approaches 1 when n grows to infinity. Another interesting sequence which will be used later when we study the root test for series. Now, I want to make an important remark. Look at this computation here. I'm finding limit of sequence, then reducing the limit of function in order to use rule of L'Hopital. You cannot use rule of L'Hopital right away because n is a discrete variable. We don't have rule of L'Hopital for sequences, we have rule of L'Hopital for functions. So first, obligatory step is to write a function, go to functions, and then you can use L'Hopital. Now, the last example for today. I want to show the sequence a sub n is natural log of n, third power over n. When we talked about rule of L'Hopital, I mentioned such things that x grows to infinity faster than logarithm x. And here we have this situation that we can use L'Hopital again and confirm this fact. I'm writing limit a sub n. This is limit natural log of n cubed over n, passing to functions, and this extends to a function, so I can write limit natural log of x cubed over x when x grows to infinity, and this is infinity over infinity, undetermined form. I can use L'Hopital now, equals limit ratio of derivatives. Derivative on the top will be 3 times natural log of x squared 1 over x, and the derivative below is just 1. X grows to infinity. Let's put 3 outside. This is 3 times limit natural log of x squared over x. Again, infinity over infinity, but it's better because the power now is just 2. Again, we differentiate. 3 times limit, derivative on top will be 2 times natural log of x, 1 over x divided by x, x grows to infinity, divided by 1, sorry, derivative x is 1. So this will be, bringing to outside, will be 6 times limit natural log x over x, x grows to infinity. You can see, you can foresee what happens next. When we differentiate one more time, this will be limit just 1 over x over x, over 1, sorry. Actually, we did this above already. X grows to infinity, so this is 6 times limit 1 over x, x grows to infinity, which is 0. 6 times 0 is 0. So several times using L'Hopital, we computed that the limit is 0. So let's write this again. Limit natural log of n cubed over n equals 0. We did this for power 3. If the power is 4 or 5 or even higher, we can just repeat the same work several steps. It will come to first power of logarithm, and then again L'Hopital, it will come to 1 over x, and the limit will be 0. So it's good to write limit natural log n to any positive power m over n equals 0. And m can be very large, but limit is still 0. Okay, enough for sequences. Please study very carefully this section. Then we go to series. If you want to understand series well, you have to be very well prepared with sequences because they're closely related. Goodbye.